Okay. Uh, so I hope you have my screen. So please let me know if there is any problem. In my previous lecture, I discussed the effect of wind and ice loading on transmission line conductors, and we reviewed how the basic sag equations apply only under ideal conditions, specifically still air and normal temperature, where the conductor is influenced only by its own weight. So we already discussed about this slide as well, and then I explore real world conditions where additional forces must be considered. In particular, we examine how ice accumulation increases the vertical load acting in the same direction as the conductor's weight. At the same time, wind pressure introduces a horizontal force acting uh, uh, preparing to the conductor. And an important part of my discussion focus on how these forces combine. And we highlighted that the resultant force on the conductor is a vector sum of vertical and horizontal components, which directly affects the overall sag and tension in the line. So we also touch on how why understanding this combined effect is critical for safe and reliable transmission line design, especially in a region exposed to harsh weather conditions and so on. So in today's session, I will build on this foundation and further analyze this, how these forces influences the SAG calculations and the conductor performance. All right. This slide showing that how wind and ice loading affect a transmission line conductor in practical conditions. On the left hand side, we can see the conductor covered with an ice layer, where T represents the thickness of the ice coating and D is the original diameter of the conductor. The presence of the ice significantly increases the overall weight of the conductor, and adding an extra vertical load acts downward along with the conductor's own weight. So in the middle figure, the effect of wind is showing, and the wind exerts a horizontal force on the conductor and acting uh, to its surface. And unlike weight and ice load, which act vertically, this force introduces a lateral component that must be considered in design calculations. And the right hand diagram is particularly important as it shows the vector combination of these forces. The vertical component is the sum of the conductor weight and the ice weight is showing by W plus Wi, while the horizontal component is the wind forces, WW. And these two components combine to form the resultant force, WT. So we have a vertical and a horizontal weight forces here, which WT acts at an angle theta by theta to the vertical. This resultant force determines the actual tension and sag of the conductor under combined loading combined loading conditions. In overall, I can say that this slide highlights that in real world scenarios, conductors are rarely subject to a single force. And instead, you must consider the combined effect of multiple forces and use vector analysis to accurately determine the mechanical behavior of transmission lines. Okay, this slide Present the mathematical formulation for calculating the total effect weight of the conductor per unit length when both ice and wind loads are present. Unlike the ideal case, here we must consider the combined effect of vertical and horizontal forces. The total load WT is can be obtained as a vector sum of these components, which leads to the this expression x squared 2 w plus wi power 2 plus ww power 2. In this equation, w represents the weight of the conductor per unit length, which depends on the material density and cross-sectional area. And the term Wi is the weight of ice per unit length. This is calculated based on the volume of ice formed around the conductor and density of ice. By considering the geometry of the ice layer, we can derive that the volume of ice per unit length is proportional to pi over 4 times these equations, or equal to t times d plus t power d plus t. And d here is the conductor diameter, and t is the thickness of the ice coating. And then WW represent the wind force per unit length. This force depends on the wind pressure and the projected area of the conductor exposed to the wind. Since the effective diameter increases due to ice formation, the projected area becomes d plus 2t per unit length, which increases the wind load accordingly. And in overall, this slide emphasizes that both ice accumulation and wind pressure significantly influence the total loading on the conductor, and the resulting combined load WT is crucial for accurately determining sag tension and the mechanical design of transmission lines under adverse weather conditions. Okay, this slide explains how the presence of both wind and ice loading changes the orientation of the conductor in space. So under these combined forces, the conductor no longer hangs in a purely vertical plane, and instead it shifts and settles in a plane inclined at an angle theta, you can see here, to the vertical. So the reason for this inclination is the simultaneous action of two forces. The vertical component is the combined weight of the conductor and ice, W plus Wi, while the horizontal component is only wind forces. Due to these components, the conductor aligns itself along the direction of the resultant force. So the angle theta that the conductor makes with the vertical can be determined using this relationship. Tangent theta is equal to WW divided by W plus WI. So this expression shows that the angle of the inclination depends directly on the magnitude of the wind force and inversely on the total vertical load. As wind pressure increases, the angle theta becomes larger, meaning the conductor is pushed further away from the vertical. Conversely, heavier ice loading also increases the vertical components, reducing this angle. All right, in this slide, I defined the sag of the conductor using a simplified analytical expression. The sag denoted by S. Last lecture, I show you this expression. Depends on the conductor's weight per unit length, the span length, and the applied tension. So, as indicated by this formula, the sag increases with square of the span length and with the conductor weight, while it decreases as the tension increase. So it is important to note that this expression represents the slant sag, which is the sag measured along a direction that makes an angle theta with a vertical. In most practical cases, unless otherwise specified, this slant sag is used for calculation. So, however, for design and safety purposes, the vertical sag is often more relevant, and this can be obtained by projecting that the slant sag onto the vertical direction, which is done by multiplying S by cosine theta. You can see like this. This is a vertical sag. Okay. This slide introduces the key mechanical principles involved in the design of overhead transmission lines. Up to this point, individual factors such as sag, tension, wind loading, and ice effects have been discussed separately. Now, the focus shifts to a more integrated understanding of how all of these factors interact in practice. And mechanical design requires careful consideration of force balance, ensuring that all loads acting on the conductor are properly accounted for our design. So it also involves understanding the relationship between tension and sag, as well as how temperature variations can cause expansion or contraction of the conductor. So additionally, external influences such as wind and ice must be incorporated into the design to prevent excessive mechanical stress. By applying these principles, you can ensure that transmission lines operate safely and maintain adequate clearances and remain reliable under a wide range of environmental and operational conditions. Okay, this slide discusses the important design consideration of tower height in overhead transmission lines. The height of a tower is primarily influenced by the span length between the two adjacent towers. When longer spans are used, fewer towers are needed, and which may seem economically advantageous at first. However, longer spans require taller towers to maintain proper ground clearance, and these taller structures are significantly more expensive to design, manufacture, and install. In addition, increasing the height of conductors above the ground raises their exposure to lightning strikes, thereby increasing the risk of outages and insulation stress. So for this reason, you often prefer horizontal conductor spacing configurations, even though they require a wider right of way. This approach helps reduce tower height and minimize lighting risks and achieve a more balanced and cost-effective design for the transmission systems. This slide emphasizes the importance of maintaining sufficient conductor clearance from the ground in overhead transmission lines. The minimum clearance must be ensured at the point of maximum sag, which usually occurs under the most severe operating conditions, such as high temperature and maximum loading. Typically, this clearance should not be less than a specified value, generally in the range of 6 to 12 meters, to ensure the safety of people, vehicles, and infrastructures below the line, so everybody can move safely. And the required clearance depends on several factors, including the operating voltage level. As higher voltages demand greater safety distances, so it should be the clearance should be higher. It is also influenced by the nature of the terrain, whether the line passes through urban area, rural regions, or uneven landscapes. So, in addition, local laws and regulatory standards must be strictly followed by designers. So, therefore, ensuring adequate ground clearance is a fundamental aspect of transmission line design to maintain safety, compliance, and reliable system operation. Okay. This slide also explains the conditions under which the maximum sag in an overhead conductor may occur, emphasizing the impact of sectional variations. The greatest sag is not limited to a single condition. It may occur during the hottest days of summer due to thermal expansion of the conductor. As temperature increases, the conductor expands, its tension decreases, and the sag increases accordingly. Alternatively, maximum sag can also occur in winter when a heavy layer of ice forms on the conductors, significantly increasing its weight and causing additional sag. So therefore, both high temperature conditions and ice loading must be carefully considered in transmission line design. And furthermore, the accumulation of ice can create serious mechanical and operational challenges, making it necessary to implement special provisions for ice removal or melting to ensure the safe and reliable operation of power lines. Okay, this slide discuss the relationship between sag and tension in overhead transmission line and highlight the importance of safety considerations during the installation. So when designing and erecting transmission lines, it is essential to include an appropriate factor of safety for the mechanical tension experienced by the conductor. So the tension in the conductor is not constant and is influenced by various environmental and operational conditions. In particular, wind pressure can introduce additional horizontal loading. Ice accumulation increases the vertical weight of the conductor, and temperature variations cause expansion and contraction of the conductor material. So these combined effects directly impact both sag and tension along the span. So therefore, you must carefully evaluate all these factors to ensure that the conductor operates within safe mechanical limits, preventing excessive stress, avoiding structural failure, and maintaining long-term reliability of the transmission system. This slide also explains how sag and tension in an overhead conductor are interrelated and how they are affected by changing conditions. So the relationship between tension and sag is not fixed. It depends mainly on the loading conditions acting on the conductor and variations in temperature. So under different environmental loads, such as wind and ice, the mechanical behavior of the conductor changes, directly influencing both sag and tension, as I told you before. So temperature also plays a crucial role in this relationship. For instance, when the temperature decreases, the conductor contracts, which leads to an increase in tension. As a result of this higher tension, the sag of the conductor decreases, and conversely, when temperature increases, the conductor expands, reducing tension and increasing sag. So therefore, understanding this inverse relationship is very essential for accurately predicting conductor behavior under varying or operating conditions and ensuring safe clearance and mechanical integrity of transmission lines. All right, this slide also highlights additional mechanical effects that contribute to conductor stretching in overhead transmission lines. Apart from temperature induced expansion and contraction, there are two other important factors that cause elongation of the conductor, and both depend on the level of line tension. The first factor is icing up of the line, where the accumulation of ice increases the effective weight of the conductor, thereby increasing the mechanical tension and resulting in additional stretching. The second factor is wind loading, which applies a horizontal force on the conductor and also increases the resultant tension in the system, whole system. So in both cases, the increased tension leads to further mechanical strain and elongation of the conductor. Therefore, these environmental effects must be carefully considered in design calculations to ensure accurate prediction of sag, maintain safe clearances, and prevent excessive mechanical stress on the transmission line components. So in this slide, I want to emphasize the key design parameters that must be considered during the planning of overhead transmission lines. So in practical engineering design, several critical quantities are selected and controlled to ensure safe and reliable operation of the line. These include the sag of conductor, which affects ground clearance and mechanical stability, the tension in a given span, which must be kept within the safe mechanical limits, and the clearance to ground, which is essential for safety, regularity, compliance, and preventing electrical hazards. In addition to this, a maximum allowable stress in the conductor is also defined to ensure that the material is not subject to excessive mechanical loading that could lead to permanent deformation of or any failure. So by carefully selecting, coordinating all of these parameters, you can achieve an optimal balance between mechanical safety, economic cost, and long-term reliability of the transmission lines. Okay, in this slide, I want to explain how transmission line design must consider extreme or worst-case weather conditions when determining mechanical stress. The main objective in planning is to ensure that the conductor stress remains within safe limits, even under the most severe environmental conditions. In cold climate regions, these worst probable conditions typically include a combination of minimum expected temperature, maximum ice loading, and maximum wind pressure. So you have to take into account these three parameters. And each of these factors contribute differently to the overall mechanical loading of the conductor. So low temperature increases tension due to contraction. Ice increases vertical loading, and wind adds horizontal forces, as I show you in the diagram. So when all of these factors combine together, this effect creates the highest possible stress state in the conductor. Therefore, you must design transmission lines to safely withstand these extreme conditions to ensure structural integrity, reliability, and uninterrupted power transmission throughout all of the system. Okay, this slide also explains the effect of wind loading on the behavior of overhead conductors and its implication for sag and clearance calculation. When wind acts on a conductor, it introduces a horizontal force that combines with the vertical forces due to the conductor own weight and any ice loading. As a result, the conductor sags in the direction of the resultant load, producing what is known as a slant sag. While wind increases the total sag along this resultant direction, it actually reduces the vertical component of the sag because part of the load is now carried horizontally. Therefore, when calculating vertical ground clearance, the effect of wind is often not included since it does not increases the vertical sag. However, wind becomes important in cases where horizontal clearances between conductors or from structures must be considered. So the distinction is essential for accurate and efficient transmission line design under different loading conditions. So this slide introduces the concept of stringing charts used during the installation of overhead transmission lines. In practical field work, it is essential to properly adjust the tension and sag of conductors while they are being strung between towers. So to assist with this process, you must prepare the graphical relationship between temperature and both sag and tension for a specific conductor under defined loading conditions. So these graphical representations are known as stringing charts. So we will see here. This is a stringing chart. Sorry, I couldn't include in this slide because text will be so smaller. So by using of this chart, you can ensure that the conductor is installed with accurate mechanical properties, avoiding excessive tension or unsafe sag condition and so on. Therefore, stringing charts play a crucial role in ensuring the correct and safe erection of overhead transmission lines in real world conditions. So this is this slide. I want to show you the stringing chart, which is essential tools used during the installation of overhead conductors in the field. So this chart illustrates the relationship between temperature sag and tension for a given conductor under a specific loading condition. So as shown in the figure, when the temperature increases, the conductor expands, leading to an increase in sag and corresponding decreases in tension. Conversely, at a lower temperature, the conductor contracts, resulting in reducing sag and higher tension. So the intersecting covers clearly here in this in the section between these two curves demonstrate this inverse relationship between sag and tension with respect to temperature. So stringing charts are extremely useful for you and the technician, as you can provide a practical reference to ensure that conductors are installed with the correct tension and sag under varying environmental conditions, thereby maintaining safety, reliability, and proper ground clearance. Okay, this slide discuss conductor vibration and the effect of wind on overhead transmission lines. Wind following across the surface of a conductor exerts pressure that can cause the conductor to oscillate or swing. So when the wind velocity is relatively low, this movement is generally harmless and does not pose a serious risk to the system. However, the key safety requirement is that sufficient clearance must always be maintained so that even during oscillation, the conductors do not come close enough to earth, to each other, or to the earth or grounded structures to reach the electrical sparking or flashover distance. So they understand me. So if the wind velocity is good enough, it can connect conductors to each other. So this is very dangerous. Therefore, while a small amplitude vibrations at low wind speeds are acceptable, proper design must ensure that adequate spacing and clearances are maintained to prevent electrical faults and ensure safe operation of the transmission lines. Okay, this slide also explains the damaging effects of conductors, conductor vibration, and protective measures used in transmission line design. While small oscillations along the span may appear harmless, the most serious damage occurs at the points where the conductor is fixed, such as clamps and supports. So at these locations, repeated cyclic vibrations can lead to mechanical fatigue, gradually weakening the conductor material and eventually causing breakage. So this type of failure is particularly dangerous because it might occur without visible warning. To mitigate this problem, vibration dampers are installed on the conductors. These devices observe and dissipate vibrational energy, reducing the amplitude of oscillations and protecting the conductor from fatigue damage. So as a result, dampers play a crucial role in improving the reliability, lifespan, and mechanical safety of overhead transmission lines. So in this slide, sorry, let me check because last time, let me check how how many minutes do we have time? So I think the time is already over. So please have a 10-minute break, and I will back to the another link. Okay, this fine.